Hi guys, in this lecture we're going to learn number theory, and this is the first lecture of number theory and the eighth lecture of the course. So in the previous courses we have seen all the others. In algebra we have finished algebra, and now we are starting number theory. And in number theory we have approximately 1, 2, 3, 4, 5. We have 5 lectures for number theory, and this is the first lecture of the first day. So every day you get 4 lectures, so it's 30 minutes, as you know, each lecture. So this is the theory class. Now we're going to do the theory class. So let's start. So a prime number. So what's a prime number? A prime number is a number which has only two factors. So as you can see, all these numbers 2, 3, 5, 7, 11, all these numbers have only two factors, which is the number itself and 1 and the number itself. So the numbers which have only two factors are called prime numbers, and 1, the number 1 is not prime nor composite. So composite numbers are except prime numbers, and 1 is not a prime number or composite number. So proof for infinite primes. So for proving infinite primes, first we'll assume. So let us assume that there are finite primes. So I'm assuming that there are few primes. So I want to prove for finite infinite primes, but I'm assuming there are some particular number of primes, and then I'm going to prove that there are. I'm going to contradict the statement. Sorry guys for the disturbance. Fine. So first I'm assuming that there are infinite primes. I mean there are finite primes, and then what I'm gonna do. So I'm gonna write n is the product of all the primes what I know. So I'm assuming there are k finite primes. So maybe it might be 100,000 or some whatever. So I'm assuming n equals to product of all the primes from p1, p2, p3 up to from 2, 3, 4, 5 up to some number. It might be very large or something. So I'm assuming there are finite primes. So now I'm taking a number q such that q equals to n plus 1. Here q is equals to n plus 1. So I'm going to write it like this. So as we know that n is p1, p2 up to till pk. So q is p1, p2, p3 up to pk plus 1. So but if you observe, when I divide q with p1, q with p2, q with p3 or q with p4, I always get a remainder 1 because p will divide this term, but p does not divide this 1, so it will leave a remainder 1. Even for p2, even for p3, even for p4 up to pk. Even pk will divide this term, but it won't divide this term. And we know that all the primes, all the finite primes, we have taken few finite primes, and none of those primes divide q. That means that even q is a prime. That means that even q is a prime. That implies q equals to prime. I hope you guys understood what I'm saying. And now p1, p2, so I'm just going to read it. p1, p2, p3, p4 up to pk does not divide q. That means it always leaves a remainder 1 because p1, p2, p3 up to pk always divides this term but not this term. So this implies that q is also prime, and we have shown a contradiction. So we got a contradiction here because we have assumed that pk is the last prime, and we have got another prime which is larger than pk. So we can prove like that it goes up to infinity. So with this proof we have concluded that there are infinite primes. So now let us look at what a factorial is. So a factorial is product of all numbers from n to 1. So you can see n factorial equals to n into n minus 1 into n minus 2 up to 3 into 2 into 1. So 5 factorial equals to 5 into 4 into 3 into 2 into 1. 4 factorial equals 4 into 3 into 2 into 1. 3 factorial equals to 3 into 2 into 1. 2 factorial equals to 2 into 1. 1 factorial equals to 1. 0 factorial equals to 1. So many people are going to get confused why is 0 factorial 1 not 0. So there's no exact proof, it's a high level concept, but for an intuition, so I can give you, so this is sequence. So I'm dividing 5 factorial by 5, dividing 5 factorial by 5, uh, then I get 4 factorial. I'm dividing 4 factorial by 4, then I get 3 factorial. I'm dividing 3 factorial by 3, I get 2 factorial. I'm dividing 2 factorial by 2, then I get 1 factorial. Now I'm dividing 1 factorial by 1, I get 0 factorial. So 1 by 1 is equals to 1. So you understand the logic here. I'm dividing it like this. So obviously by this logic I get 0 factorial equals to 1, and there are also other proofs which are highly advanced, what you do not require. So now here, what is Legendre's formula? So in Legendre's formula, if I want to, so listen to my statement, if I want to find the number of factors, the number of, okay, so here's a small example. So I want to find the power of 2, I want to find the power of 2 in 16 factorial. So by Legendre's formula, the Legendre's formula will exactly give us this. So if you want to find the power of a prime in n factorial, then you can use this formula which is given right here for finding. And now let me tell why this works. So let us just solve with an example. So 16 by 2 plus 16 by 4 plus 16 by 8 plus 16 by 16 plus 16 by 32, and the greatest integer function of all these. So anything after 16 by 16 is always 0. So when I take the greatest integer functions of all these, I get 8 plus 4 plus 2 plus 1. This is 12 plus 3 equals to 15. So even though you actually manually check it by multiplying, you get the same thing. So one thing what you need to observe is, let me just write it here. So let me show, so if I have a number 20 factorial now, so I'm just multiplying 20 into 19 into 18 into 17 up to 3 into 2 into 1. So how many numbers are divisible by 2? There are 10 numbers alternatively which are divisible by 2. 20 factorial, 20 by 2. So all the numbers like 20, 18, 16, all these are divisible by 2. But if there's a number which is divisible by 4, then we get an extra factor of 2. So now, what are the numbers which are divisible by 2? 4, 8, 16, 12, 20. So there are 20 by 4 numbers. There are 5 numbers which are inside the 20 factorial, which are divisible by 4. And similarly, we have to check whether some number is divisible by 8, because 8 has an extra factor of 2 than 4 by 8, then plus 20 by 16 plus etc. So this is the logic why we're doing this. I hope you guys have understood. So there's always an extra factor of 2 in a higher power of 2, like 2 square, which is equals to 4, has higher factor of 2 than 2, because 2 into 2 equals to 4. So that is exactly why we are dividing it by n, then n square, then n cube. Just a second guys, I'm just erasing these. So, and all the notes would be in the Google Drive link, I mean the Excel link what I've sent, and this will be already posted in Udemy if you're seeing it from Udemy also. So trailing zeros. So what exactly a trailing zero is? So a trailing zero is nothing but a number which has n, which is n. Let us assume a number, assume a number n such that maybe it's something in the form of 1 3 1 2 3 7 2 0, something like this. It has a 0 at the end, so this 0 is called a trailing 0. So if this is 0, if it's like this, these are not trailing zeros. The trailing zeros have to be at the end. So let us consider a number 10. So I can write this one as 1 2 3 1 2 3 7 2 into 10. So I'm obviously right. So this 10 can be written as 2 into 5. So if it is 0 0, this is 100. This is nothing but 2 square into 5 square. So the number of trailing zeros depends upon the zeros. This depends upon the number of 2's and 5's. So if I have a number n equals to 2 power 4 into 5 cube into 3 power 3. So the number, it depends upon the number of 2's and 5's. So 2 cube into 5 cube gives me 3 zeros, and then 2 into 3 cube, which is nothing but 2754,000. So a pair of 2 comma 5 gives us 1 0. So we cannot get a 0 with any other factor like 3 7 9, 3 7 11 13, whatever it is. So the number of factors. So I have a number here. I have a number which is in the factorized form of p1 into p1 power a1 into p2 power a2 into p3 power a3, so on. So the number of factors in this number n is a1 plus 1 into a2 plus 1 into a3 plus 1, so on. In the number of odd factors, for the odd factors you just need to remove this, and then you need to just write. And why do I need to remove this? If the first number is 2, if p1 equals to 2, then you need to remove 2. So if there's no factor of 2 in a number n, then you don't need to remove 2 because there's no use, because you don't need to remove the first factor obviously. So because all the numbers are going to be odd because there's no 2. So if I'm considering a number with the first factor as 2, which is p1 in this case, so I'm not including p1 plus 1, I mean a1 plus 1. Similarly, if I want to find the number of even factors, then I gave here, as you can see, I have taken out the 1 here. So you just need to take out that 1. So I'm going to prove all this now. I'm going to prove, don't worry about that. And the sum of factors is kind of looking like a GP. So this is like the sum of GPs, right? Sum of GP. So sum of GP. So it's nothing but the first prime, which is here, this one, in power a1 plus 1 minus 1 by p1 minus 1 into p2 power a2 plus 1 minus 1 by p2 minus 1, so on. So let me explain you the proof. So the proof is quite simple. So I'm going to write the number of factors as p1 power 0 plus p1 power 1 plus p2 power 2 plus so on. You can see that I have a1 here. So I'm just writing a1 as 0 1 2 3 up to a1, and for others also, for a2 also I'm going to write p2 power 0 p2 power 1 so on till a2, and for p3 also. So in this case, when you multiply all of them, you get all factors, all different possible types of factors. Like if you want to find a factor which is 1, so then you need to take p1 power 0, then p2 power 0, then p3 power 0, so on. If you want to find the number n, then take p1 power a1, p2 power a2, then p3 power a3, and so on. So in this case, I want to list out all the factors. I'm listing out all the factors. So all the factors here are p1 power. So if you take all the factors of, all the numbers, all the powers, all the sum of the powers of p1, which is nothing but p1 power 0 plus p1 power 1 and so on till p1 power a1. So here you can realize that there are a1 plus 1 number of terms, and here there are a2 plus 1 number of terms, and here there are a3 plus 1 number of terms, because From 1 to a1 there are a1 terms, and 0 is also included, so you will have a1 plus 1, so on. That is why this formula exists. That is why we get a1 plus 1, a2 plus 2. So now if you want to find the number of odd factors, so I'm assuming this is 2 power 0, 2 power 1, 2 power 2. So if you just remove this one, if you just remove this term, you get a2 a2 plus 1 into a3 plus 1, and you're not considering this for a moment, so that time when you do the product of all these terms, as you know there's only one prime number which is even, which is 2. So all these, the product of all these is going to be odd, that's for sure, 100%, because 2 is not even included anywhere. So that is why we are not including a1 plus 1 here. So we directly get a2 plus 1 into a3 plus 1, so on. And now let us come to the even factors. So this one exact case where we are getting odd. So now I'm including this. So when I include the two powers, which is 2 power 1, 2 power 2, 2 cube, 2 power 4, 2 power a1. So only this number, which is, so it is like 1 plus 2 square plus 2 cube, so on, and I'm multiplying this. So only this number, when this is multiplied by this term, then I get something like p2 cube into p3 square, and this is odd. This is odd because the factor of 2, which is 2 power 0, is getting multiplied here. So instead of 2 power 0, this is something like 2 power 1 or 2 power 2, then this whole thing will become even. So that is why I'm excluding, this time I'm excluding 2 power 0. So because I'm excluding 2 power 0, it becomes a1 into a2 plus 1 into a3 plus 1, and so on. And as you can see, it's pretty obvious, the sum of all factors, as I have told in the previous class, sum of all numbers in a GP, you can see this is a GP, this is a GP, and this is a GP, and the formula for GP is written here, written here, written here, simple. So you have to remember this proof, because this proof is gonna help you in problem solving. I am really sure this will help you, because sometimes they might ask, find the number of numbers which are divisible by 15. So find the number of factors, find the number of factors which are divisible by 15. And if n is a really big factor, you can't just factorize all of them and then try to divide it by 15, then 30, then 45, all that. You can't do all that bullshit. So you got to think in a smarter way, and this proof will help you. And I'm going to solve those kind of questions in my second lecture of today, which is the basic lectures, the basic problem solving. Then after that we'll be having advanced problem solving. Then you will be having previous year questions of AIME, AMC, IOQM, which is India, AIME and AMC, which is US. And if you're from another country, so you can still watch this, because this will also help in your because I'm only familiar with India's and US competitions, like India, Canada, Australia, British, and India. So I'm only good with the knowledge of these Olympiads and the way they go. And I'm pretty sure that all the other country Olympiads, like Balkan Olympiad, Iranian, China, even those exams for the first stage, you're gonna have of the same level, which is of IOQM or AIME or PRMO level. So let us go to the next slide. So cyclicity. So just a second, guys. So what is cyclicity? So cyclicity is something, so you can understand by the name itself. It is like a cycle. So it's going to repeat again and again. So observe 1 power 1. 1 power 1 has a units digit. Sorry, here it is I. You can see, there should be an I here. So the units digit of 1 power 1 is 1. 1 power 2 is 1. 1 power 3 is 1. So on. And now if you observe the units digit of 2, there's a change in 2. 2 power 1 equals to 2, 2 square equals to 4, 2 cube equals to 8, 2 power 4 equals to 16, but I'm going to take the last digit, which is 6. And 2 power 5 equals to 32. I'm going to take the last digit, which is 2. You can see 2, 4, 8, 6, and we're getting back to 2 again. And again, we're going to get a 4. So you can see it's going to repeat again and again. So you can see that after 4 numbers, you're getting another 2. So the cyclicity of 2 powers is 4. So you can see I've given the cyclicity as 4. And now let us take for 3. So 3 power 1 equals to 3. 3 square equals to 9. 3 cube equals to 27. I'm taking the last digit, 7. 3 power 4 equals to 81, which is 1. Again 3 power 5 equals to 3. 243, I'm going to take the last digit. You can see after 4 numbers, 1, 2, 3, 4, and getting a repeated cycle again 3. So cyclicity is 4 again. Let us look at 4. 4 power 1 equals to 4. 4 square equals to 16. 4 cube equals to 64. 4, 6, and again we're getting a 4. So the cyclicity is 2, because after 2 numbers we're getting the third number, we're getting the repeated one again. So if you observe a 5, 5 power 1 equals to 5. 5 square equals to 25. I'm going to take the last digit, which is 5. 5 cube equals to 125. I'm taking the last digit, which is 5. You can see it's always 5, 5, 5, 5. Just like 1 we have here. So it's always 5. The unit digit is always 5. And now let us consider 6. So just a second, guys. So cyclicity is a really important concept, and when we combine it with divisibility, we're going to get the remainders. So these questions there are many IOQM, AIME, AMC previous questions like these with this concept, and this will really help you a lot. Guys, and try to watch the whole lecture, because you're going to get the knowledge of the math Olympiad only if you watch the whole lecture, not like going to watch for 10 minutes and wait for half an hour, wait for like more 20 minutes and then watch 10 minutes and take break. You got to watch the whole lecture at a time, and then you're going to go to the basic problem solving, and then advanced, then previous year problem solving. So let us look at 6. 6 power 1 equals to 6. 6 square equals to 36. 6. You can see it's becoming always 6. 6 cube equals to 216. Again a 6. So it's again always 1. And similarly for 7 power 1, 7 square, 7 cube, and 7 power 4, 7 power 5, 7 power 6. Later I'm going to write more now. 7 power 1 is 7. 7 square equals to 49. 7 cube equals to 343. 7 power 4 equals to 2401. Again we get 7 power 5 equals to 7. After 4 is getting repeated again. After 4. So we are having 4 unique values here. So the cyclicity is 4. So you can even understand the number of unique values in the powers of a number. Like in the power of 7, you have 4 unique values in the unit digits, which is 7, 9, 3, and 1. So you can say the cyclicity is 4. So cyclicity equals to number of unique digits. So this is another way to understand. And then for 8 also, 8 is nothing but 2 cube. So we'll have 8, then 64, then 512, then 512, then 2 into 8, which is nothing but 6. So we get 8, 4, 2, 6. And again after 6, 6 into 8 equals to 48. So we're going to get it repeated after 4 numbers again, which is cyclicity 4. And now if we look at 9, 9 power 1 equals to 9. 9 square equals to 81. 9 cube equals to 729, which is 9. So whenever I get a 1 here for odd numbers, so after that 1, when we now multiply the number itself, so I get the number. So 1 into 9 equals to 9. So 1 is a really good number in cyclicity, and it's also going to help us in other concepts also. So that's all for cyclicity. Cyclicity is a really easy concept, but many people see it in a tough way. So try to understand it in an easy way. And guys, if I'm going too fast, or if you don't understand, you just gotta watch the lecture again. You just go back and start watching again. You don't need to think, oh, I'm not understanding. Many people, according to my knowledge, are already watching it for the first time or even second time already. So divisibility. So these are some divisibility rules what I've just copy pasted. If you're having a problem in any of these, so this is just a concept what you learn in 4th or 5th grade. So you can just go through these concepts I have just given for the lecture, I mean for the notes purpose. You can just go through this in your free time or after the class, or you can pause it right now. So remainders. So in remainders, you got to use cyclicity plus divisibility. So these two will be giving us awesome question for like all these Olympiads like AIME and IOQM, China Math Olympiad, all those exams, and the concept of negative remainders. So I'm gonna explain this now. So what exactly a negative remainder is? So I have a number 18 and I'm gonna divide it by 5. So when I'm dividing it by 5, I write 5 plus 5 plus 5 plus 3 and divide by 5. So these numbers are divisible by 5 and this number is not divisible by 5. So I say the remainder is 3. What if I think in a reverse way and I write 18 as 20 minus 2 by 5, and you can see that 20 is divisible by 5 and the remainder is minus 2 now. So the remainder when 18 is divided by 5 is 3 or minus 2, any of these. So let me give another example. So I have 37 and I'm dividing it by 7. So the remainder is 2. I'm writing it as 35 plus 2 by 7, or 42 minus 5 by 7, which is minus 5. So if I have a number and I'm getting the remainder 2, and if I'm dividing it by 7 example, so if I want to find the negative remainder, I'm just subtracting 2 from 7, I get minus 5. This is a short trick. And another one, so let R1 equals to positive remainder, and R2 equals to negative remainder, then R1 minus R2 equals to n. So example, I have a number 18. So let us take the number 18 and I'm dividing it by 5. The positive remainder is 3 and the negative remainder is 2, and 5 is my n. So 3 minus of minus 2 equals to 5 and 5 equals to n. So this is the concept of negative remainder, guys. And LCM of and HCF I have given this for the notes purpose as well. You can go through this. So this is the first lecture of number theory, guys, and this lecture is really basic. And in the problem solving, in the basic problem solving, we're gonna look at all the examples of all these concepts. Plus, we're gonna look at some little higher level problems, and in the advanced level, we're gonna do kind of like the PRMO level questions, but which have been given in PRMO or IOQM or AIME. And in the fourth lecture, we are gonna actually do the previous year questions of those. So I hope you like the lecture, guys. Thank you.